Alright guys, welcome back to part 2 of the periodic trends lecture. If you have not already watched the first lecture on periodic trends that I put up, I would encourage you to go and watch it now before viewing this lesson. For this lecture we're going to be discussing periodic trends of ionization energy. We'll then be talking about electron affinity, and finally we're going to take a brief summary on metals versus nonmetals. So let's go ahead and get started. So our first topic here is going to be ionization. And when we deal with ionization energy, we can define ionization energy as the energy input that's going to be required to remove an electron from the valence shell of a given atom. So remember, our valence shell is our outermost shell, or it's going to be the quantum number where the electron resides. So you guys remember quantum numbers, n equals 1, n equals 2. Also remember that removing electrons from a valence shell is going to promote cation formation, because when we lose an electron, we take on a positive charge. So remember, when we draw our cations, we put a plus charge, and that plus charge is representing a loss of electrons. So we can really view ionization energy as the ease of cation formation. How easy is it for us to form a cation with a given atom? And we relate these two, we would say that the lower an atom's ionization energy is, the easier it will be for it to form a cation. And this makes sense because electrons that only require a small amount of energy to remove would be removed readily and they would form cations. It's also important to realize that atoms can have more than one ionization energy. For instance, magnesium would normally carry a 2+ charge, and so we would need to ionize magnesium twice in order to do this. So let's take a look at a table of ionization energies. So right here we have a table with multiple ionization energies for the third quantum level, starting with sodium. So remember, quantum level, we're talking about n equals 3. So if you went down 3 rows in the periodic table, you would be here. And we can see here that sodium would require an energy of 498 kilojoules is the unit. I'm sorry that they don't have the unit on this table, but it would be kilojoules. So it's 498 kilojoules in order to remove an electron from sodium. And we know that sodium normally would be Na+, so it does tend to lose one electron. Now look what happens. If we move down the chart, you can see that this number tends to increase as we're moving down this way. So as we go down period 3, we see an increase in the first ionization energy. Now there's some breaks in this trend that we're going to explain. So let's take a look. For one thing, when we jump from magnesium to aluminum, which are the second and the third atom on this table here, when we jump from magnesium down to aluminum, we see that there's a bit of a discrepancy in the ionization energy. It actually drops for aluminum, even though the general trend is to increase as we're going down. So how can we explain this? Well, this break in the trend can be explained in the fact that it requires more energy to pry an electron from a S shell than it does from a P shell. And that's because S shells are slightly closer to the nucleus, and therefore they're a bit more stable since they can feel the positive charge from the nucleus. And this accounts for the energy drop that's going to be seen as the first electron in aluminum would be removed from a P shell, and the electrons found in magnesium only reside in an S shell. So that can account for that discrepancy and that small drop of energy there. So next we keep going, we're going down, and then we can see a small drop when we look at phosphorus and sulfur. So if you take a look there, phosphorus and sulfur, the phosphorus has a kilojoule requirement for its first ionization energy of 1063, and then the sulfur is only 1000. So the drop isn't quite as drastic as it was for the magnesium and aluminum, but we still have a drop we need to explain here. And we can explain this because the phosphorus has 3 unpaired electrons in the p orbital. Remember, you have the degenerate equal energy states, and where we get to phosphorus along the p shell, it has 3 electrons, so there's 1 in each orbital, and none of the electrons are paired. That's a very stable formation because it's going to minimize the electron repulsion. Now if we go to sulfur, Sulfur has one set of paired electrons. We have 4 electrons into the p shell when we get to sulfur, and so I have to pair up one of those sets. And because sulfur shows some of that electron repulsion, it's going to be slightly easier for me to remove. Not much easier, but slightly easier for me to remove an electron from sulfur versus phosphorus. And then we start outdoing that once we get to the halogens, because we're approaching noble gas state, which is very stable. So there's 2 other things that I want to examine on this table as we're looking at trends. First, look at what happens to the energy of ionization when each subsequent electron in a valence shell is removed. It greatly increases. So if you take a look at magnesium, you can remove the first electron for only 736 kilojoules. But then the next one costs 1,445 kilojoules. That's a large jump. So you can see this increase in energy costs all the way across the table as we go. So take a look at aluminum, 577, 1815, 2740. And then you go to silicon, 787, 1575, 3220, and then 4350. We're increasing with each one. So what is that telling us? It represents that when you have each atom and you're removing another successive electron from it, you're going to have to put in more energy. And that makes sense because as we continuously remove electrons, we're making it less and less stable. We're increasing the charge on the atom. And so it's going to require more and more energy in order to get the next electron in the valence shell out. Now there's a second thing that I want you to notice with this table, and that's the orange colored break that you find in the table that's about halfway through. And what this orange colored break represents is where each atom would be retreating past the valence shell, and you would start attempting to remove electrons from a completed core shell. So we're retreating back. When you get into that orange level, you're talking about trying to remove electrons, in this case from the 2s or the 2p shell. And that is going to be very, very costly. And you can see the large energy jumps when you get into the orange region compared to the white region that you had to the left. So why is this happening? This is a highly destabilizing process to the atom. So what you're essentially doing is you're attempting to remove electrons from a noble gas state because you've already sealed off that quantum 2 level, or whatever quantum level has a core electron in it. And it's going to be incredibly expensive. You're going to have an astronomically large energy fee for removing electrons that are already stabilized and set up in those prior core energy sets. So let's move to the next one. Here you can see sort of a recap, but this is a nice table because it lays it out in terms of the periodic table. So this table is going to show just the first ionization energies. And I want you to note the energy discrepancy at the end of the S shell and the start of the P shell. So remember, we were saying that the S shell, it requires a little more energy at the end of the S shell in comparison to the start of the P shell, because it's easier to remove that one electron sitting in a P shell compared to the S shell. And we can see that discrepancy. Beryllium 899, boron 800, magnesium 738, aluminum 577. Calcium is going to be 590. The gallium is 579, and you can continue downwards, and you can see as you're going across there each of those trends. So there's another one. We can also see the trend that is halfway between that is in between the halfway filled up p orbital and when we start pairing electrons. So right here, if we go 3 electrons into the p orbital, you see nitrogen, phosphorus as you continue down, and then if you look across, look at oxygen compared to nitrogen. We're dropping down close to 100 in our energy requirement. And this discrepancy that we see as we move across here is due, again, to that electron repulsion as we start pairing up. Now, we ditch it once we get to the halogens because that's getting very close to a noble gas. So getting close to that noble gas configuration is greatly increasing the energy requirements because we're getting more and more stable as we move across. But that first pairing there, you can see a slight discrepancy. And something else interesting to note, you can also note that the noble gases here, look at how high their ionization energy is, and we sort of mentioned this previously. This is because of their stability. They absolutely do not want their electrons being touched or removed. They are already in a stable octet. Helium's not an octet, it's a duet because of the 1s shell. But they're in a very, very stable state. And so therefore it would require a huge amount of ionization energy to come in and grab any valence electrons from any of those noble gases. So let's do a very brief recap. Let's look at our takeaway notes here. Ionization energy for core electrons is going to be very high compared to those of valence electrons. So that's the first thing we want to note. That was that orange break in that table. And the other thing we want to note is that breaks in the trend occur between shell types, so S to P, when we go from the S orbital over to the first electron in the P orbital, and then when we have electron repulsion that occurs within an orbital. So we were looking at that P, where the nitrogen-oxygen was breaking, where the phosphorus-sulfur was breaking, etc., as we go down there. All right, so let's continue on. The general trend, what's going to be the general trend for ionization energy? Ionization energy is generally, now we've already noted our exceptions, it's generally going to increase as we go across the periodic table, and that's due to an increased effective nuclear charge. So what does that mean? It means the tighter that an atom is going to hold on to its electrons, the more energy I would be required to spend in order to remove those electrons from that atom. And that makes sense. So again, go back to lecture 1 if you haven't seen it, or if you need a refresher on effective nuclear charge, because it helps explain some of these other trends. And so what can we say about the ionization energy going down? Well, we can say that ionization energy will decrease in general as we move down the periodic table. And this is due to an increase in the radius size. So we know that as we're going down the table, we're adding more and more shells. The radius size is increasing. That's going to further remove the valence electrons from the nucleus, and it's going to make those electrons easier targets for removal. So that, in general, is our summary of ionization energy. So now we're going to move to electron affinity, and I'll just warn you guys, electron affinity is sort of the most difficult one in terms of the trend. It's sort of all over the table, but we can come away with one general trend when we're working with this. So let's just talk about it. So for electron affinity is the last of the major trends, and it refers to the ability of an atom to draw electrons towards itself. So in a sense, it's almost the opposite of ionization energy. Ionization energy, we're seeing how easy is it to remove electrons from an atom. And in electron affinity, we're trying to measure how easy it is for an atom to gain electrons. So electron affinity is measured by the energy released when an atom picks up an electron. The more energy that is released, the more beneficial it was for the atom. That means the atom was in a very high energy state, and when it picked up an electron, it helped to stabilize it, so it became lower in energy. So the larger that energy release, the more beneficial it is for that atom. And therefore, the higher the atom's electron affinity will be. Things that release a lot of energy when they get an electron, it means they desperately wanted that electron, so they have a high electron affinity. And by the way, the term affinity, hopefully you guys know, affinity means a draw towards or a desire for. So we're talking about an atom's desire for picking up extra electrons. Now, many of you have heard me discuss the concept of electronegativity in class. And we're going to talk about electronegativity in a lot of detail in the next chapter when we start doing Lewis structures and the theory of bonding. But for right now, I'll just mention there is a strong correlation between electron affinity and electronegativity. So finally, we should note, you can see at the bottom here, it says, the noble gases appear to break this trend, where the trend, they tend to participate in the other trends, but they're going to break this trend. And the reason behind this is that the noble gases have a complete, electronically speaking, a complete shell, and so they have no desire to pick up additional electrons. They're not going to have an affinity for electrons because they have all the electrons that they would want. All right, so let's go ahead and proceed here. So what you have here is an electron affinity table, a general electron affinity table. Note that the values here, a lot of them are negative. And remember, the negative is representing the direction in which the energy is being either absorbed or released. If it's negative, it's being released. So the values that are negative are energy being released upon obtaining electrons. So if you have a negative value, you have some extent of electron affinity. If it's not very beneficial for an atom to pick up an electron, the value is going to be close to 0, so it might be a small negative number, or it's going to be greater than 0. And you can see this is very evident in the noble gases. We just talked about this. So there's no electron affinity, or at least not a very strong electron affinity, for the noble gases here. And you can see throughout the chart pretty low numbers for the cations, the metals, and that tends to make sense because these form plus charges. These guys would also form plus charges, so they might have a slight electron affinity, but it's going to be very, very weak in comparison to the right side of the periodic table there. So again, very evident with the noble gases. Electron affinity is, as I mentioned ahead of time, it's by far the most complex of the trend sets. We can make one general statement here, which is that electron affinity tends to increase in general. Again, there's exceptions. It tends to increase across the periodic table from left to right, minus the noble gases. So look at the halogens. The halogens here have very high electron affinities. We go one step back to the oxygen and sulfur row. Here, nitrogen tends to skip out on this trend. That's because it's got some other factors that we're not really going to discuss here. But notice that these guys are also smaller because they have, again, each of those individual electrons that aren't paired with the electron repulsion. And so, therefore, it's in a pretty stable state. They're not quite as eager to go around picking up electrons and pairing them. Whereas oxygen and the halogens, they are pretty close to the end game. They want to get over to the noble gases. So if we take a look at just this general statement here, a higher electron affinity means a better ability to form anions. And that makes sense. An atom that can draw electrons to itself easier or pick up additional electrons has a greater chance of forming negative charges or anions. So what is the general trend that we can sum up for electron affinity? Electron affinity will generally increase as we go across the periodic table. The up and down is a bit too complicated. We're not going to discuss it right now. But as we go across the periodic table, we're going to have an increase, a general increase in electron affinity. Remember, we're excluding the noble gases here. So noble gases participate with ionization energy, electron affinity, but here we're going to have a bit of a break there because the noble gases do not want to pick up extra electrons. But this general process can still be understood through effective nuclear charge, because as we go across the table here, we're drawing our electrons closer and closer to the nucleus, and therefore the nucleus can have a greater draw for additional electrons trying to come in. So let's finish this up, talking about metals versus nonmetals. This is just going to be a very quick summary here. Metals, they tend to have a shiny luster to them. They are very good conductors of heat and electricity, whereas our nonmetals tend to be poor conductors of heat and electricity. Most metals are malleable, and what malleable means is it's readily shaped. So sometimes we may have to melt down the metal to shape it, but it can retain a certain shape we put it into. Whereas a lot of the nonmetals, if you took solid sulfur or something like that, or the gases, you can't really put them into a shape. They would either crumble apart fairly readily, or they don't even really have a shape. If you have the gases, they are going to expand to fill the container that they're in. If you take a look, most of the states for metals are solid, with the exception of mercury. And then when we look at the nonmetals, we have solids, liquids, and gases. The liquid for the nonmetal, if we're looking just from the elemental side, would be bromine, but there's lots of nonmetal molecular compounds, such as water, that could also be liquids. In general, our metals have very high melting points, fairly low melting points for the nonmetals. In fact, some of them are gases at room temperature, so we would have to retreat pretty far back. You look at something like how cold liquid nitrogen is. And then finally, what we want to certainly mention here is bringing it back to the periodic trends. We have low ionization energy for metals. That means they can form cations very easily. We can get rid of some of those electrons. And then in the opposite sense, most of the nonmetals have high electron affinity, and therefore we can form anions when we're dealing with most of the nonmetals. So that's just a little summary chart there. So as always, thank you very much for watching. Please remember to like the video if it helped. I always look forward to your comments if this helped, if you have any critiques or ideas. And then please remember to subscribe. It's the easiest way to find upcoming information. So thanks a lot, guys, and I'll see you for the next lecture.